Welcome to The Explainer. I'm absolutely thrilled you're joining us today because, honestly, we're about to unpack something truly groundbreaking. We're looking at a fascinating new preprint from Dr. Melvin Sewell over at the Cosmic University of Echo Rift Studies. It's titled, A Segmented Systems Architecture for High-Frequency Asymmetric Multiplexing in Large Language Model Edge Robotics. I know, that sounds incredibly dense, a real mouthful, but what we're actually talking about here is a massive, fundamental leap in how artificial intelligence controls physical bodies in the real world.
Okay, let's dive into this. Here's the central conflict we're looking at. Right now, we have these incredibly brilliant high-parameter large language models. These foundational reasoning brains that can write poetry, code software, all of that. But when you take one of those brilliant brains and put it inside a multi-jointed cybernetic platform, a physical robot, they suddenly cause the hardware to stumble, hesitate, and literally freeze up. It's like you've got a super smart but relatively slow semantic brain trying to drive this fast, highly reactive physical hardware, and they just clash terribly.
Here's our roadmap for today's journey. 1. The robot brain bottleneck. 2. The arthropod inspiration. 3. The three-tier architecture. 4. The strobe core protocol. And finally, 5. The future of cybernetics.
Starting off with Section 1, the robot brain bottleneck.
So, forcing a complex cybernetic platform to rely on just one single monolithic LLM core, it causes severe systemic processing latencies. Dr. Sewell calls this first major barrier operational processing isolation, but honestly, let's just call it what it is: brain lag. Think of the LLM as the CEO of a company, and the robot's physical motors as the factory floor. The CEO is up there doing all this complex, high-level reasoning, but their speed fluctuates depending on how hard the thought is. That's the fluctuating token generation speed. Meanwhile, down on the factory floor, those motors need instructions every sub-millisecond just to keep the robot from falling over. So when the CEO takes too long to think, the motors just stall out waiting for validation. This uneven data load creates instant localized hardware instability.
Then we hit the second major barrier, which is data interface desynchronization. I personally like to think of this one as sensory blindness. See, without an intermediate layer, an edge robot's camera arrays and sensor clusters are trying to stream just this massive amount of high-definition spatial data directly into that slow, deliberating central model core. And the core, it simply can't process all that dense visual data while it's busy thinking. The result is severe visual frame dropping. The robot's eyes essentially freeze while it waits for its brain to catch up. And as you can imagine, that is absolutely catastrophic if the robot is trying to navigate a volatile, fast-moving environment.
And this brilliantly illustrates the core of the problem and exactly why we need a solution. On one hand, we have the failing monolithic core approach. When you centralize everything, you get severe telemetry bottlenecks, massive data containment issues, and you even hit thermal propagation limits because the system is just totally overworking a single node. But the paradigm shift here is the segmented architecture. We absolutely need decentralized buffers, we have to decouple that deep thinking logic from the physical actions, and we need completely isolated motor loops.
Moving right along to Section 2, the arthropod inspiration.
To solve this brutal microsecond latency problem, Dr. Sewell realized that nature actually figured this out millions of years ago. He looked back at early evolutionary biology, specifically at Cambrian arthropod ganglia structures, and it's truly wondrous when you think about it. These ancient multi-leg bugs didn't use one single slow central brain to control every micro-movement of their legs. I mean, if they did, they would have been eaten long before they could even take a step. Instead, they relied on highly decentralized neural layouts. It's basically nature's way of ensuring the physical hardware never ever has to wait on the software.
By studying these bugs, we get this perfect biological blueprint for robotics. This natural design completely avoids localized processing fragmentation. It utilizes segmented ganglia loops, which basically means clusters of nerves handle local movement right there at the leg without checking in with the main brain for every single twitch. By translating these biological segmented loops into software code, a modern robot can completely bypass those centralized bottlenecks for raw motor control. It just reacts, instantly.
Which brings us to Section 3, the three-tier architecture. So Dr. Sewell took this biological inspiration and mapped it into a strict algorithmic stack. At the very top, we have the executive core. That's our LLM. It only handles high-parameter logic and long-term semantic task planning. It's the big thinker. Down at the bottom, we have the edge telemetry sensor thread. This guy handles the sub-millisecond raw mechanical manipulation, operating totally independently. And sitting right between them, acting as the ultimate peacemaker, is the translation buffer layer.
This concentric stack safely and beautifully, honestly, decouples the slow token generation from those lightning-fast motor executions.
I want to focus just for a second on that middle layer, the translation buffer, because its function is absolutely critical. It continuously reconstructs ambient spatial arrays from the sensors and compresses them into what are called flattened topological matrices. Basically, it instantly translates dense, chaotic real-world sensory data into a super lightweight, highly compressed format. This ensures that when the inner executive core finally reaches out for an update, it gets a clean, immediate snapshot without triggering a thread lock block. The sheer speed and efficiency of this process literally eliminates the brain lag we were talking about earlier, keeping the whole shebang flowing smoothly.
Let's look at how this works in practice in Section 4, the Strobe Core Protocol.
Now, what's really interesting here is how these layers actually talk to each other without stepping on each other's toes. Notice the term high-frequency temporal asymmetric multiplexing, which the researchers very brilliantly nicknamed the strobe core. The absolutely crucial point is that the robot is not trying to do everything at once. Attempting continuous, uniform multi-thread calculation, that's exactly what causes the system to stall. Instead, the strobe core protocol isolates a semantic thought process from the hardware execution by multiplexing its attention millions of times a second in alternating cycles.
It breaks down into these two very specific alternating rhythms that completely prevent that cognitive desynchronization. Step 1 is the anchor routine, and step 2 is the asymmetric multiplex routine. Just back and forth, boom, boom. Let's look at exactly what happens in each of these high-speed steps. Step 1, the anchor routine, happens in a microscopic millisecond operational window. The system establishes a hard thread lock with all the physical hardware metrics. It ingests the environment arrays right through its sensory registers, evaluates critical planning states, and then the hardware microcontrollers confirm all the loop parameters. Literally, in a mere fraction of a blink, the system locks in and checks the absolute physical reality of the robot.
Then, immediately after that, in the very next clock cycle, we hit Step 2, the asymmetric multiplex routine. Here, the two ends of the robot decouple. The high-level executive brain is released to run its heavy semantic planning completely asynchronously. And at the exact same time down in the hardware, the low-level motor microcontrollers are executing their stored physical vectors entirely independently. The physical movement completely bypasses those main executive thread bottlenecks. By strobing back and forth between these two states millions of times per second, the physical body never waits on the slow brain, and the slow brain is never ever overwhelmed by the physical body. Which brings us to our final section, Section 5, the future of cybernetics.
So, what does this actually mean for the big picture? Well, this isn't just some fun theory. The structural abstraction mapping and the mathematical proofs in Dr. Sewell's preprint demonstrate that this architecture actually works. It guarantees cross-platform software stability, even in highly volatile, high-noise, real-world environments. It prevents the systems from hitting those dangerous thermal limits and ensures total structural stability for autonomous physical hardware. This is huge because it successfully takes AI out of the sterile computer environment and safely drops it into the physical, chaotic world.
The ultimate takeaway from Dr. Sewell's research is profound. He concludes that this segmented architecture is a scalable template for the future ancestry of autonomous robotic automation infrastructure. We are literally looking at the foundational DNA for the next generation of robotics. By solving this brain lag problem, we're finally unlocking the ability to put the most advanced, high-parameter LLMs into dynamic, fast-moving machines safely and effectively.
It really leaves us with a fascinating paradox to consider, doesn't it? We are pushing the absolute boundaries of artificial reasoning, creating minds of just incredible complexity. Yet, to successfully give those minds a body, we had to look hundreds of millions of years into the past. So I'll leave you with this to ponder. When will our most advanced, futuristic robots finally learn to think like an ancient bug? Thank you so much for joining me on this explainer. Keep exploring, keep learning, and we'll see you next time.